So 3.1, introducing the derivative. Now we are slowly moving to the main part of calculus. Calculus is basically based on two things, derivatives and integrals. And this is the first part of that. Fortunately, I mean, you guys are fortunate that uh, you don't need to go really deep into the integral part in this particular course. Um, I guess they have covered the entire derivative part and just the basic idea of integration. I've seen previous calculus materials, from the spring or fall semester. So that's good for you because integration is huge and it has so many different categories. It takes a lot of time. So anyway, so let's start derivative. And before that, we want to see what does a tangent. What does a tangent
A
do?
tangent is just a line that can anywhere along a graph. It's the line that essentially touches at one spot just briefly and then continues moving right?
Yeah, yeah, that's right. At a particular point, you can only draw one tangent here because a tangent line um, can just touch one point on the curve. Obviously, you can have several tangent lines, but it will be on several points. So, what does the tangent line give us? It actually gives us an idea which way the graph is going, or which way. Well, let me say it this way. Let's say you have a path. Okay, you have a path. Um, this is the starting point, and this is the end point, and you want to go from this to this place using this path. Okay, let's say this is the um, best possible way you can use to reach this place. Now, let's say if Toriano asks you that, hey, which way you are going when you are just at this position, just at this position. He wants to know the instantaneous uh, position of you or instantaneous velocity of you. He could ask you to uh, find or to tell him the instant results at a particular point, at a particular position. So tangent will help us to find that. So if you draw a tangent at that particular point, it will actually tell you exactly which way you are moving, you are walking. Okay. So for example, if you are just at this position when I have the cursor, if you draw a tangent line there, you can see the tangent line is showing us this way. That means at this particular position, you are actually heading towards this direction. That means the trajectory of the moving object can be found from the tangent. Okay, we'll see more of this. Let's see what we have next. And if we need, then we'll come back to that. Okay. Okay. We already know uh, how does the secant line work, and if we move, you know, obviously for drawing a secant line, we need 2 points, right? If you remember. Now, if the 2 points move really close to each other, eventually it will fall onto each other and it will become 1 point, right? We know that. I mean, if the 2 points converge to each other or move really close to each other, right? And if that's the case, we say that's not that's no longer a secant line, that becomes a tangent line, right? So this is what we have. So we know the secant line has the definition of this. I mean, if you have 2 points, let's say at A and at T, then the definition of secant line, we know that uh, the slope of the secant line, my bad, the slope of the secant line, we know that the functional value at that point, the difference of the functional value, and the difference of these values. So S of t minus S of a. S of t is this bluish circle, and S of a is this bluish circle. So that's the difference. The difference between these two is this part of the straight line divided by the difference of these 2 points, t minus a. We know the definition of the slope of the secant line, right? Now, as I said, if these 2 points converge to each other, moves really close to each other, that means if t tends to a, or if t approaches to a, right? This point is moving really close to this. So in that case, we have the slope of the tangent line, right? We know the definition of this as well. And we can actually find the instantaneous velocity by that. And why? Again, this is the distance the moving particle would cover, and or you could say the displacement, you might rephrase it. And this is the time interval, all right? Because we have mentioned that on the x-axis, I mean, we have mentioned it as t, we have the time duration, and on the s-axis, we have the position. That means the distance it's covering, right? So the displacement over the time is actually the velocity. So this will give us the instantaneous velocity because it's actually considering a really, really close, I mean, considering displacement and time intervals of really, really close 2 points. So this will give us the instantaneous velocity. Now, why do you need this even though we are trying to introduce derivatives? You will soon see. Okay, so let's say, not this one. Yeah, this one. Okay, let's say we have an interval from a to x. It could be anything, as you know. We had from a to t here, right? We'll come back to these graphs, no worries. Okay, and in this interval, we know the slope of the secant line is this, the functional value, the difference of the functional value over the difference of the independent variables, right? And we have already seen how does the instantaneous rate of change work, because when the 2 points move really close to each other, then it converges to each other, and we say it's the slope of the secant line, tangent line. I apologize, slope of the tangent line, and this gives us the instantaneous rate of change, right? We've already seen that on the graph. Now, we want to derive the equation of the tangent line from this. Now, can we do that? Let's try. Okay, so equation of the tangent line, if we try to do that, will be this. So we can move this or rather we can cross multiply this on our left, right? So this will become slope of tangent line times x minus a, right? And f of x is basically y, isn't it? If we define our function as y equals to f of x, that's what we generally do, then f of x is basically y. So on our right, we'll have y minus f of a. So if I can rewrite it, this becomes this. Y minus f of a equals to the slope of the tangent line times x minus a. And this is the equation of tangent line. You'll need it. You'll need this equation several times in the homeworks and obviously in the exam as well. I'll give you 2 points and say, hey, can you find the equation of the tangent line? And you just need to use this formula, plug in the values. Every information will be provided. If one of these is missing, the information which you will need to find that will also be given. Okay, you'll soon see examples of it. So you need to remember this. You need to remember this formula. Okay, y minus f of a equals to the tangent, the slope of the tangent times x minus a. Okay. All right. Let's see the graph. So this is the graph of y equals -3/4 times x plus 3. Okay, now I mean by this I mean the red line. Okay, and the curve is the graph of y equals 3/x. Now we want to first we want to find the slope of the tangent at this particular point, 2,3/2. We want to find the slope at this point. Okay, so since nothing is given here, what we can do, I mean, obviously for finding the slope, you need more information, right? Okay, now since nothing is given, graphically what we can do, we can draw a straight line like this. You can draw a straight line like this at that particular point where you're trying to find the slope of the tangent line. Okay, and this line will be the tangent line, right? So if you can find the equation of that, if you can see where does it take you, then you can then using this formula you can find the tangent. I'm telling you the probably the most difficult question from this. I mean, the graph is given and you are asked to find the slope at a given point. This point will be given 2,3/2 or whatever it is, the point will be given, but nothing else. Nothing else will be given. You'll be asked to find the slope of the tangent line at this particular point. So graphically what you can do, you can draw a straight line just touching that point. And then if you can just find the equation of this straight line, then you can find the slope using this. If you can rewrite the equation, then you can get this. So how can you do that? Okay, so this line, if you draw it, if you will see this line is going through this point 0, 3. This one, can you see the cursor I'm moving? if you add this, and you will see that it actually goes through this 0.03. So that means whenever x is 0, this graph goes through this 0.3, y equals 3. And we know, if you remember, from the standard equation y equals mx plus b, where b is the y-intercept, we know that y-intercept is the point, or rather is the length, you might say, when x is 0. On this occasion, it will be 3. So that's how the 3 comes, okay? And now, you can just use these points in the y equals mx plus b equation. And if you solve it, you'll get a negative 3/4. Just you can use these points. Y will be 3/2, x will be 2. So it will be m times 2 plus 3. If you solve it for m, you'll get a negative 3/4. Now, we know that this m is the slope of the tangent line, because we know y equals mx plus b, m signifies the slope. So we can tell that the slope of the tangent line at this point will be negative 3/4. Okay? Is it too difficult? If you want me to re-explain, I can do that for you, or I can show you the calculation if you want. Anyone?
Could you just show the calculations of finding just
Yeah,
the
sure.
slope? I understand the y-intercept, but just the slope part.
Sure, of course. Let me share the screen. Okay. So today is 3rd. So, okay. So we know the general formula of a straight line is y equals mx plus b, where m is the slope and b is the y-intercept, right? We already know the y-intercept is 3 from the graph. We can see that. So technically, we actually have mx plus 3. So now the only thing we need to find is m. And for that, we have one more information which you can use, is this point. So let's do that. So y will be 3/2, right? 3/2 equals to m times x will be 2 plus 3. So 3/2. Okay, let me show the step. No worries. 20 plus 3. If I just change sides like this, this doesn't change the value. It keeps the value intact. So I can do that. And 2m now becomes 3/2 minus 3. I've just added negative 3 to both sides. If I simplify it, I'll get 3 minus 6. That's a 6/2, or a negative 3. Really? Wait. Did I do anything wrong here? Let me see. It was the point 3/2. 2 and 3/2. Yeah, that's right. 2 and 3/2. Okay, so 3. Oh, sorry. Yeah, I can see what I did do the mistake. This one. This is -3. Sorry about that. Yeah. So this is -3/2. And if we divide both sides by 2, we get -3/4. Okay, so this is the calculation. Any question from this? You'll probably see a question like this. Maybe not, because generally I tend to give you more information. This graph doesn't have too much information. Anyway, yeah. Any question from this?
No, that makes a lot more sense. Thank you so much. I just had to see it.
Oh, okay, no problem. All right, so this is the graph. Okay, I think we have seen this graph before. Yeah, we have seen this graph in 2.1. This one as well. We are at this graph, so let's see what we have next. Okay, yeah. All right. Now, instead of showing it as 2 different points, what we'll do, since I'm sharing the screen, let me have the pleasure of showing the graph. So instead of showing as 2 different points, let's say A and X, now we'll do it this way. We'll show that this is A and this is A plus H. Okay, A plus H. And we want to find the instantaneous rate of change. And if we find it, first of all, we need to know the corresponding functional value, right? So these are the corresponding functional values. And now, if we add these two, it was not a straight line. Now it looks more, yeah, now it looks like a straight line. Okay, so this gives us the secant line, slope of the secant line, right? So this is the slope of the secant line. Okay. And we are definitely trying to find the slope of the tangent line. Okay, someone is in the waiting room. Give me a second. Okay, yeah. So that means we are basically trying to find what's happening at this point. Sorry. At this point, this is the slope of the tangent line, right? Okay, so we are looking for this one. So what we need to do here, again, we just need these 2 points to move closer to each other, right? That means these points, instead of being here, it moves closer and closer to the corresponding functional value of for A. It moves closer and closer to that. And if it's really, really close to this functional value for A, then we can say that it's no longer 2 more points, 2 points. Instead, it can be assumed as 1 point, and it can give us the slope of the tangent line if we can draw a line there, right? Okay, and for that, what else we need? We need this to be really, really close as well, right? Since the graph is moving this way, I mean, it's getting closer and closer to this point. These 2 points has to be closer to each other as well. Okay, so here we have moved from A to A plus H. If it goes really close to each other, can you imagine what can happen? This will take us when H will be really, really close to 0. Do you agree? Because I'm saying that A and A plus H has to be really, really close to each other. The only difference between these two is the H. So if these two moves really close to each other, that's possible only when H tends to 0. H is really close to 0. Do you agree? Anyone? Any concerns about it? I'm just reiterating the same thing, just we have seen in the previous graph, nothing else. Since we are trying to go to the definition of derivative, okay? So initially, if you remember, we had the slope of the tangent line as limit x tends to a, f of x minus f of a, x minus a, right? That's the initial definition we have. But instead, now we want to write it this way. Limit, I'll write the limit later. Let me write it here. So the first one is h, because this is the difference between 2 points, right? What's the difference between these 2 points? It's h. Can you see that? And it's the functional value a plus h minus f of a. So this means the 2 points are getting really close to each other. That means the difference is getting close to 0. So this time the limit will be h tends to 0, because this is the difference. Okay, we want to write it this way. I'm just rewriting the previous equation, nothing else. Okay. All right. Now, why do you even need that? Why do you even need that? So we need this because this is actually the definition of the derivative. Okay, so we say, let me start sharing the screen again. There you go. Okay, so we say that at a point A, if we're trying to find the derivative, we just need to find the slope of the tangent, because the derivative actually gives us the instantaneous rate of change, nothing else. The first derivative, of course. This is the first derivative. We denote it by f prime. This signifies, when you write f of a, this signifies the functional value of a. If you write f prime of a, that means it's the derivative of that function at a. Okay, you are evaluating the function, the first derivative of the function at a. Okay, so this is the mathematical formula of the derivative of a function at a given point. Okay, and again, you'll need this because I'll give you a function and say find the derivative of this function. If no point is given, you can find the general derivative of that. Okay, I'll show example of it, no worries. But if a point is given, then you can evaluate the derivative at that point as well. That's not difficult. The difficult part, if any, is actually calculating this. You'll soon see examples of it. And you will definitely see questions, at least one question, where you will be asked to find the derivative using this formula. And often it's tricky, it's difficult. Okay, it's true. It's true that it's often a need. It often needs some technical calculations. You'll soon see examples of that. Okay, but again, you'll need to remember this formula. If I'm allowed, I'll provide this formula, but that's less likely. I'll ask the course coordinator anyway. Okay. If he says that I can do whatever I want, I'll definitely provide the formula, because memorizing the formula won't be doing any good. Rather, you need the technical knowledge, how to formulate this and how to simplify this, right? Okay, so this is the formula you'll need. Next, okay, so this is the graphical representation of the first derivative, although you'll be asked, in most cases obviously, you'll be asked to do it algebraically. That means this function will be given. Okay, this is your function. This is f of x, you might say. And for this function, you'll be asked, not this one, sorry, my bad. This one, yeah, this is your function. Y equals square root of 2x plus 1. And for a function like this, you'll be asked to find the first derivative or the derivative at a given point, let's say at 2. Excuse me. So you need to use this formula and then evaluate that at 2. Okay. I'll try to avoid the graphical part of the question because it doesn't actually make sense, because it doesn't require you to do any or rather implement any concept of a derivative. If you are doing it graphically, maybe it actually is more of the equation of the straight line. If you can use that, you will be able to find it. Rather, I'll tell you to do it algebraically. Okay. Okay, so let me see if they have it. Yeah, so yeah, that was the basic idea. So they actually didn't go any didn't show any example and didn't go too deep into this. They just kept showing different graphs. So I don't think you need any more graph, because it's literally the same thing, drawing a straight line to find the tangent or the slope of the tangent. Okay. Instead, I want to show you some real examples. So let's start 3.2. And if we need to go back to any of these graphs, or if you have any questions from any of these graphs, just let me know. I'll be more than happy to go back. Okay. But again, these graphs are all the same, of different functions, nothing else. Any question from these graphs? If you have one already, you can ask it. Okay, seems like no questions, so we can move on. And again, you will see these graphs won't be necessary as long as you know what's happening here. And we already know what's going on here, right? Again, we'll come back if we need. Okay, now let's see the sign of the derivative or the slope of the tangent line. So if you can draw a tangent line at a given point, let's say this one on our right, okay, and if you can join it with the x-axis, if you can just extend this line with the x-axis, if the angle created with the x-axis is more than 90 degrees, in degrees of course, not in radian. If it's more than 90 degrees, then we say the slope of the tangent line is negative. Okay, and you can clearly see the function is going downwards. That means the instantaneous rate of change is getting decreased. So you can clearly see, even algebraically, the value is, if this is the peak, this is the highest point you can reach, then you can see now the value is getting smaller, right? That means the change is going in the backward direction, or it's actually getting smaller. So it's, if you consider it with the highest point, it will be negative. The graphical representation, as I said, if you can extend it and join it with the x-axis, if the angle with the x-axis is more than 90 degrees, then we say the slope of the tangent line is negative. Okay, or the first derivative at that point is negative. Okay, what happens if the angle is less than 90 degrees, like this? If we have drawn a tangent line at A, not at A, I mean at the corresponding point for A on the graph, on the curve. So if we can extend it and join with x-axis, and if the angle is less than 90 degrees, then we say that the slope of the tangent line at that point is positive, or the derivative at that point is positive. And you can clearly see, again, this is the highest point. You can eyeball it from the graph, and you're slowly and slowly going there. So definitely you're getting increased, your values are getting increased. So that's why it's positive, right? Excuse me. Obviously, if you're considering with this, right, the difference will be positive. Okay, now what happens if it's neither? I mean, if it's not creating any angle which is neither less than 90 degrees nor greater than 90 degrees. So we can actually have two different cases, although they didn't show the other one. I'll tell you briefly. One possible case could be if you can just draw a tangent line, and if you see that that line is basically parallel to x-axis, like this one. If you draw a tangent line at B, at the highest point, you can see this reddish line is parallel to the x-axis. Do you agree? And if that's the case, you can never extend it and connect it to the x-axis, can you? Because it's parallel. It will always be parallel. Two parallel lines can never intersect each other, right? Now, the next question could be, then what's the angle between these 2 points, these two straight lines, the x-axis and this slope? What's the angle between these two? Anyone?
180 degrees.
And why do you think like that?
Because it's a straight line.
Okay, anyone else? Do you agree with him? That's the first question. Do you agree that the angle should be 180 degrees?
Yes.
Is there anyone who doesn't agree? Okay, now since the angle between these two lines, I mean x-axis and the slope, is, you are saying that you agree that it's 180 degrees. Now can you tell me what's the value of tan 180 degree, tangent of 180 degree? I'll soon tell why am I asking it. But can
Is
you
it 0?
0, exactly. Now, since we are finding the slope of the tangent line, we actually, with the angle, we actually calculate the value of tangent, tangent of that angle. So if we go back to here, this angle was greater than 90 degrees, right? So if you take any angle greater than 90 degree, and obviously it has to be less than a 180, because if it's 180, it comes to this point, right? So if you take any angle which is in between 90 to 180 degrees, you will see the corresponding tangent value will be negative. You can check it. Try plugging in 91 degrees in your calculator, or try 150 degrees. You will see all the values will be negative. Okay, and if you try any angle which is less than 90 degrees, the corresponding tangent value you'll see it's positive. Again, you can cross-check it. Okay. Okay, so the two angles between, the angles between two parallel lines is either 0 degrees or 180 degrees. So whatever it is, if you plug in tangent of 0 and tangent of 180 degrees, either way you will get a 0. So that's the 0 here. Now, what does it mean graphically? Well, you can see it's the highest point, and if you just try to find the change at that particular point, you will see that it's not really changing, because at this point you will see this is moving this way, At this point, you will see this is moving this way, but this is the highest point. So at that very point, it's not really moving to any way. It will take a halt there, and then it will start going downwards from the next instant. But at that instant, it will not change because it has already reached the highest point. So graphically, whenever you see a graph at the highest point, well, obviously, if the point before that is increasing and after that is decreasing, then at the highest point, you will see the derivative will always be 0. But obviously, it might not be the case always, because you will see some exceptional cases as well. But again, as I said, if before the highest point, the graph is increasing, and after the highest point, the graph is decreasing, then at the highest point, the derivative will always be 0. And vice versa as well. I mean, if it's upside down, the graph looks like a cup, like this, like a U, then at the lowest point, the graph will also be 0 for the same reason. Okay, all right. Now I'll briefly tell you the other case, and then we'll go for the break. They didn't show it though. I have already said what happens if the angle is between 0 to 90. What happens if the angle is from 90 to 180? What happens if the angle is 0 or 180? But what did I miss? What did I didn't say? Which angle I didn't include? Anyone?
Greater than 180?
Sorry? Oh, greater than 180 is basically the same, because again, if you just make it upside down, it will work the same way as it has worked on the upper half of x-axis. So the way it behaves for 0 to 180, it will behave the same way for 180 to 360 as well. But which angle I didn't include at all?
Was it the angles less than 90?
No, this is the angle less than 90, right? I didn't include the angle 90 itself, did I? So if you see a graph, and obviously if you try to draw a tangent line which goes straight into the x-axis. I mean, when you draw a tangent line, if you can extend it, you see that it goes straight into the x-axis. That means it's creating a 90-degree angle. Then we say the derivative does not exist at that point. Okay, that means there is no
We can't understand you. Something happened to your mic.
I still can't hear you at all.